Hey everyone, I am Rohan, and today we will see a short demo on our VLN circuits design. So we know that for VLN circuit design, the most important circuit is a CMOS inverter. CMOS inverter. So we will start with that. We'll learn what is transformer of a CMOS inverter. So we can see in the left hand side, a CMOS inverter consists of a PMOS and an NMOS in series, and the current of PMOS and NMOS plus as they are in series will be equal. So first of all, to have the transfer curve, we first have the input and output equations from our CMOS inverter. From the circuit, we can see for NMOS, for our NMOS device, what can we say? For NMOS device, we know that this is our gate terminal, the source terminal. So if we say the gate to source voltage of our NMOS will be equals to our input voltage of the CMOS inverter, and this is our drain terminal. So we can say this is our drain terminal, this is our source terminal. So the drain to source voltage of our NMOS will be equals to V out of our CMOS inverter. So we have already this equation. Similarly, we can write for our PMOS device. So for PMOS device, what can you write? So we know this is our gate terminal, again, this is our gate terminal, and this is our source terminal. So the VGS of our PMOS circuit will be equals to, so as gate voltage is equals to VIN, so it will be equals to VIN minus VDD. And for similarly, if we want to find the VDSB, so we know this is our drain terminal and this is the source terminal, so it will be equals to in it will be equals to V out minus VDD. So we have successfully found all the equations of our NMOS and the input and output equations of our CMOS inverter. So for writing the so here we will now start writing the voltage transfer curve. So what is a voltage transfer curve? A voltage transfer curve is a curve between the input voltage of our CMOS inverter and output voltage of our CMOS inverter. So we have got the equation now, right? Our curve. So for the curve, we know there is two axes. One axis is y-axis, the y-axis, and our x-axis. So in x-axis, we will plot our input voltage to the our CMOS inverter, and in y-axis we will write the output or CMOS inverter. So first of all, we have to find the critical input voltages that will turn on and off our NMOS and CMOS circuit. So for the first thing, we know there will be a region, there will be a voltage input will threshold voltage of our NMOS voltage, because below this the NMOS will be turned off, and there will also be a let's say gate threshold voltage. There will also be a voltage that will be equals to VDD minus mod of VDP, because above this voltage level the PMOS will be turned off, and finally there will be our input voltage can be as high as VDD. So we have marked down all the critical input voltages. Now we have to find the operating regions of our NMOS, of our NMOS and our both PMOS. So we have to find this. So how can we find this? So we know for NMOS, for our NMOS, we know it will be in saturation when the drain to source voltage will be greater than over drain voltages. So we can say the VGSN is equals to VGSN minus VTN, threshold voltage. But we already know that drain to source voltage is equals to V out and gate to source voltage is V in minus VTN. So what can we do? We can write a straight line. So we can draw a straight line from there, and above this straight line, our NMOS will be in saturation, and below this straight line, our NMOS will be in linear. Similarly, we can do this for our PMOS too. So there can be a PTP. So we know for what will happen for PMOS, and right for PMOS. So what will happen for PMOS? For PMOS, the V out will be E equals to V in minus PTP. So we can write another straight line that will be like this, then like this, and above this straight line, our PMOS will be in linear, and below this straight line, our PMOS will be in saturation. So we have successfully marked out the operating regions of our PMOS and NMOS. Now, so from this we can have some regions carved out like this, right? And the last one. So what can say? We can say this is our region A, this is our region B, this will be C, this will be D, and last of all, this will be our region E. So let's start with the region A. So let me get this for region A. For region A. So what is there for region A? We know in region A the input voltage is less than our threshold voltage of the NMOS. So our NMOS is off. So what can we say? This in this region our NMOS is turned off. So as our NMOS is turned off, we can we can model the overall the overall CMOS inverter as the PMOS will be in resistor and the NMOS will be open circuited because there will be the NMOS will be turned off. So we can see the output voltage will be exactly equals to VDD. So what can we say? So this is our output voltage when our input voltage is less than V threshold. Right. So let's move on to our second region, that is our region B. So in region B, what will happen? In region B, we can easily see that in our region B, our PMOS is in linear. We can say from our PMOS is in linear, and our NMOS is in saturation. So as our PMOS is in linear and NMOS in saturation, we can turn this into a current source because we know when the PMOS and NMOS in saturation, they work like a current source. So this is our equivalent circuit for region B. So we can see if we increase the V input a little, input to match the current in our PMOS circuit, the VDD minus Vout should increase. So for that reason, the Vout should decrease. So we can say the Vout will decrease like this in our B region. So let's move on to our C region. So in our C region, we can see our PMOS and NMOS. That means in this region, our PMOS and NMOS both are in saturation region. So as both are in saturation region, what will happen? That our PMOS and NMOS both will work like a current source. Current source. So and if we increase the voltage a little, there will be a large voltage drop. So you can increase like this, right? And then I think the curve should be a little bit better there. So okay. Now we have moved on to our region D. So we can say in our region D, what happens? In our region D, what happens? In region D, the PMOS in saturation. You can see the PMOS in saturation. So we can write PMOS is in saturation and our NMOS in linear. So as NMOS in linear region and PMOS in saturation region, so we can model the PMOS as a current source and the model the as a resistor. So what will happen? So further our voltage will decrease this, like this, and then we have finally came to our region E. So what will happen for region E? We can see that in region E the input voltage is greater than VDD minus VDP. Here VDD minus VDP. So while the input voltage is greater than VDD minus VDP, the and PMOS will turn off. What will happen? The PMOS will turn off. So we know the VIN is greater than VDD minus mod VDP. PMOS turned off. So as PMOS turned off, our equivalent circuit will look like this. And this is our Vout. So we can say our what will happen to our Vout? The Vout will be equals to zero voltage. So this is the transfer curve of our of a CMOS inverter. We have seen it by region by region. So okay, let's write in region. PMOS is off. Right. So this is our overall transfer characteristics of our CMOS inverter. Thank you, everyone.